So I know that the headline of this tech session is no high-level vagueness. However, I will inflict you 2 minutes of business pitch or marketing pitch just to introduce you to Schroders and also tell you what business case we have solved, because at the end of the month, we are all paid to solve business cases and not to play with machine learning tools. Schroders is an asset manager. Actually, is the largest asset manager listed in UK. Are you all familiar with what a discretionary asset manager is? Because I had no clue before joining Schroders. Any of you? No? Okay. So, asset manager means that we get money from our clients and we invest them in the financial markets. Discretionary means that we don't have deep neural networks or algorithms making these decisions on which stocks we buy or sell, but we have humans. I mean, we have fund managers that discretionary choose which stocks, which companies are good and which companies are bad, and what to buy and what to sell. However, they don't make their choice just by sticking a finger in the air like this, but they make choice informed on data and analysis. So this is where our team, which is a data insights unit, comes into play. Our mission is to bring scientific rigor to all discretionary business decisions in Schroders. So, among the other things, we bring on board alternative data sets that can shed light on particular companies, on particular aspects of a company that fund managers are interested in. And we also offer tools that fund managers use in order to make better decisions, hopefully. Some of the time series that we bring on board look like this. I mean, I'm not allowed to tell what they are, but I can say that they are related to some of company features that our fund managers are looking at daily. Of course, a change in any of these features can trigger a decision to buy or sell a stock. So it's quite important for a fund manager to be able to detect changes or trends in this time series. Obviously, since we bring tens of thousands of time series every day, our fund manager can't spend their whole time just staring at this data and deciding when something interesting happened. So they asked us to be told only when something relevant happens. So we had to build a tool that detects a change and automatically alert them, hey, something interesting happened, maybe you need to buy or sell the stock. This is a business case. So given this problem, we actually thought, well, that's banal. I mean, of course, we have a time series. The time series will have a certain standard deviation that we can more or less calculate, and then we check when new data are outside the 2 sigma, and okay, this is something interesting, and end of the story. Well, actually, is not the case. I mean, I invite you all to try this simple method, and you will realize that you will brutally fail immediately. So normally, when you have a problem, it's very likely that people much cleverer than you and me have already solved it, and maybe they also have published it. And if you're lucky, you also find somebody else that very kindly put on GitHub somehow some decent code that you can reuse, or at least at least that you can use as a starting point for what you have to do. So in my case, I just Googled online change point detection. I got some reasonable results. Then I added the Bayesian word in front because it sounded much better, and I found this great paper. And lucky enough, the implementation on GitHub was actually in Python, which is the only language that I know. So, bingo. So, what is the paper about? So I really loved it because it has very, very simple assumptions. So it assumes that a time series can be segmented into chunks that we call runs, and the data within each of these segments is IID, but it doesn't make independent, identically distributed. But there is absolutely no restriction on which distribution they follow. I mean, they could be following a Gaussian distribution, it could be Poisson, binomial, it could be a count, it could be TD student, long tail, we don't care. Anyway, they just need to be IID. So it's a very loose assumption, which I really like. And the very interesting thing is that what they do is that they want to model the probability of run length. So imagine that you are at time t here, so here time is 5, and you want to calculate, actually let's write an equation just to be more precise. You want to calculate what is the probability that at this point the run length or the length of the segment is 5, 4, 3, 2, 1. Well, sorry. Well, I start from 1. So exactly. So at each time point t, you want to know the probability of a run length after having observed all the data. So it seems very, very intuitive. So what is before going through the algorithm, I just want to show what is the output. The output is this. So this is the original time series, and here we have a matrix that tells what is the probability of a run length at a certain time t. So in each pixel, if it's darker, it says that the probability of a run length of, I don't know, 200 in this case, is high. So this means that when we are more or less here, it says that the most likely run length is about 300, meaning that the segment started here. When you are here, it shows, well, actually, it is likely that the run length is 600, so that the segment started here. However, there is also a good chance that it started much later. So it started around 200 data points before, so here. I hope this is clear what we are trying to do. So if you expand this equation, you will find like 3 terms that you need to calculate or impose. So the first one is what we call the change point prior. So this you can think about it as what is your expected average length of the segment. So if you expect more or less a segment to be long, I don't know, 100, 150 data points, you will put a prior that will give you roughly this. The second term that seems to be very, very innocent here in the middle, it tells the predictive probability of a new data point for each possible previous run length. So this seems easy, but you will immediately realize that since you need to do it for each possible previous run length, if you are at time 1,000, you need actually to calculate 1,000 different predictive probabilities. So for each run length, so well, let's take the example of 4 instead of 1,000. When you're here, you need to calculate what is the probability, the predictive probability of the new data point if the run length is 1, so if it's only this data point, or if it's 2, or 3, or 4, and so on. So this can be a computationally very expensive thing to do. And finally, you need to weight everything by the probability of the previous run length. So I'm sorry if I've lost half of the audience, including myself, in equations, but the nice thing is that in the code, it looks really, really, really simple. I mean, all this process are literally, 10 lines of code and some nice comments. So I invite you to, well, either read it from here or just go to GitHub or Google and find the original version that we somehow adapted. Okay, so this is now the output of the algorithm. So we ran the algorithm. We are very happy with the results. I mean, it shows that, for example, here, something probably happened, more or less. Maybe something happened also here. But if we give this to our fund managers and we tell them that, I don't know, in April 2015, more or less, maybe there was a change. Maybe the time series increased. And then in October 2016, there is a certain probability of something changes, but maybe not. Well, I mean, our fund managers do not care about the probability of regime change. I mean, what they care is that they want to be told when something has really happened. I mean, they're not Bayesian. I mean, so I thought, okay, like, or our Bayesian castle is collapsing and so on. But actually, no. We had actually this pushed us to do something more than what we found on the paper. We had to extend it, and we had actually to find what is the most likely path. I explain what it is in a second. So you know that at each time point you could either continue the segment or you reset and you start a new one. So altogether, if you have t time points, you have about 2 to the power of t minus 1 possible paths, which is a number that becomes rapidly very, very, very large. So if you want to compute what is the most likely path, well, you can try brute force. I mean, we tried, and when we got to 20, basically, well, it was absolutely unfeasible. So we had to do something smarter. And so one of us, not me, thought about a much better way to approach this problem. So the matrix on the top is simply the probability of rank length at the time. So time is on the x-axis. And you see that basically it's like seeing this matrix here, like these pixels here plotted as a matrix. I mean, there's nothing else. The next step is to calculate the log probabilities, because we are going to sum them up. So instead of multiplying the probabilities, we sum the log probabilities. And the rule, so the second stage are just the log of what is up there. And in the last bit, actually, we have what is the cumulative log probability path. This means that if you, at each time step, if you want to increase the segment length, you just need to sum up this number to this number, and you obtain the probability of run length 2. But then at the next step, two things could happen. I mean, it could happen that you reset, or it could happen that you continue. So you can convince yourself that you can solve this problem with two simple rules. So one is that on each diagonal, you just cumulate the log probabilities. Well, actually, when you reset to 0, so it means that a new regime starts, you always fall from the point which had the highest probability. I mean, it took me a while to make sure that I understood it. If you got it right now, it means that you are really fast. We can talk about it later if you don't, if you need explanations. So, what are the results? So from this, that our fund managers don't really appreciate, we go to this, and this is something that is actionable. This is something that I can really use. You see that in the top time series, so we also show the best fit, and with the vertical lines we show when the change was detected. So you see that this first change, since it's actually quite tiny, I mean it's not a big difference, it took quite a lot to the algorithm to realize that something really happened, because it had to accumulate evidence. But when something more drastic, more rapid happens, actually the algorithm reacts immediately. So it's exactly what we would intuitively expect, and this is what also our fund manager understands well. So I can show you a couple of other examples. So you see that this algorithm works well also in a case where the variance of the signal changes a lot. So there, towards the end, in the second stripe, you see that the variance increases a lot, but the algorithm doesn't care. I mean, can deal with that. And only at the very end, when not only the variance increases, but also the mean increases, then it will react. So it's quite robust to this. It's also robust to different distributions. So you see this is an absolutely horrible distribution, but still can deal with it very well because we modeled it correctly. So I was quite impressed when I saw the results. So I will just play very quickly a video to show just one example of what happens in real life. Okay, so this is the algorithm at work live with the time when the thing were detected. So, okay. I will not play another video. So view, enter full screen. Okay, here we are. So this is our stack. So we coded everything in Python. Everything is version controlled in GitLab. We have Jenkins that manages and runs all the jobs every night on about 20,000 time series. It prepares, it dockerizes the code and ships it to EC2 instances, and where all the magic and calculation happens. And after that, we get the data back to our servers, and we write it in Microsoft SQL servers. I'm sorry for that. After that, we have another job that actually reads the data and sends automatically the emails to the fund managers which are interested in the change. And we got actually very, very good feedback from them. So conclusion. So first, we learned that like simple problems are usually not that simple, but at the same time, there are smart people that already published the solution, or at least something that you can start with, and maybe they also have implemented or sort of implemented it on GitHub. And also that academic papers are absolutely great, but usually they don't give actionable answers. I mean, you need to go that extra mile, and also this is why it's fun, and this is why we are here, because it's not just implementing something that somebody else did, but you need to adapt it and make it useful, actionable. At the same time, you also need to always have in mind how you will run it in production. And the reason is that we could have used much more complicated methods based on Gaussian processes, jump processes, or other stuff that maybe works, maybe better, maybe not, but that they would have been extremely slow. And so in real life, we wouldn't be able actually to run them daily and to have a fast update. So always think about how you will run in production. Thank you. Well, and we are also hiring, just in case.
Any questions?